let's do a very quick discussion on thermal oxidation. hmm Now, I'd like to show you one important picture. It's an electron microscope image, and you will see similar images, hopefully, when you examine TEM and SCM in the following week. But this is now what you're seeing is the interface between a thermally grown oxide and a silicon substrate. It's always very striking for me because I don't see any huge irregularities between the two. That is why we actually work with silicon in the first place, because silicon, as the most commonly used semiconductor, can grow its own oxide. So we do not need to brutally try to grow, deposit a new oxide on the top, but it kind of grows its own oxide on the top. And I can see one more drastic thing. I can count the atoms here on the silicon side. As you can see, they are the single crystalline structure, whereas at the top for the amorphous, I don't see that kind of a nice continuation of a network. So that crystallinity has been lost there, as you can observe. And that's going back to our first lecture, the difference between the amorphous and crystal structures. All right, so why do we need an oxide layer? Because in the first place, silicon is nice. We can play with its conductivity. That's what I was trying to emphasize over these lectures. As a semiconductor, you can tune its properties by playing with temperature, by playing with dopant levels. All those are fine. You can work around with that. But then when you build your devices, you like to also create an insulating layer too. You like to have some portions that will be isolating the other portions. For that reason, the oxide will be very, very handy. And of course, by now, I'm sure you already know that when you find a wafer just sitting all by itself in a clean room, that will not be an immediate silicon wafer. There will be a very, very likely a native oxide. This is too thick. Actually, it's gonna be going up to 2 nanometers or 3 nanometers, less than 5 nanometers for sure. But there will be a very thin layer, and it's gonna be residing there, waiting for you. All right. So that's the first oxide. It's just natively grown oxide. It's just grown by itself. As for the other types of the oxide, we've talked a lot about MOSFETs, right? We said that they were our switches, so we could conduct or not conduct based on the third electrode that we had on the gate. So with respect to the voltages, we were enabling the conduction or not. In this case, this transistor as the fundamental block of all of our computation and all the science today, we need to have super good high quality gate oxides just underneath the gate. And the importance is, here is another electron microscope image. So you can see the thickness of the gate oxide here. It's only 0.8 nanometer thick, or 8 angstrom thick. So we have the gate as the polycrystalline silicon in this case. So I can see some arrangements of the atoms, but it's not going to be like the crystalline silicon where I will end up with what we call the grain boundaries. As for the silicon, I have a fully nice arrangement here underneath. And here I again end up with the amorphous material that I was emphasizing. Okay, what other types? Well, we built our transistor, but we like to isolate our transistor from its neighbors. So there might be another transistor like here. In between those two, you'd like to put these kind of isolation centers. So they're going to be the field oxides there. And we'd like to also isolate these, let's say, these new electrodes that you're trying to create, new conductive electrodes, from the underlying conductive electrode. That's going to be another source of use for the oxide. After all, it's mainly for isolation. That's the main purpose that we're using it for, but there will be a couple of other uses as well. So this is how we isolate and how we create these kind of structures here. Again, in the older days we were using the local oxidations, locos, and now people are switching to, or already switched to, shallow trench isolation because it's plainer. But the main idea is very similar in terms of isolation. And again, this is just showing you how you can grow these isolation sites, but I'm not going to emphasize that. Another use of oxide is for masking. So that's another critical use. So you see, we're going to introduce our dopants, highly energetic ions, from the top onto our silicon wafer. And we'd like to block the penetration of these ions into silicon in certain regions. We'd like to allow it somewhere. We'd like to block it somewhere. Silicon dioxide is a nice material for that, for this masking purposes. As you can see further, we have these used as more barrier oxides. So we are enabling non-conduction between the two electrodes. Like these could go to jumpers here, and these two electrodes, the two signals, will not be shortened to each other thanks to the oxide. Or we can try to smooth out the locations to, like you can see here, this pad oxide as a thin oxide. Its main purpose is to cover on these kind of areas to smooth out the whole trajectory for the upcoming layer, so that once you deposit the new layer, it will see not this kind of a sharp change in terms of the topography. You see, this is really a huge slope here. It might break and it might create these kind of stress on the side walls, and that might actually put a lot of tension on that little thin layer there. But if you, on the other hand, if you put a thin layer of a pad oxide to smooth out those regions, so it's going to be, of course, better than this first example. So it won't really see those kind of sharp corners. Okay, so based on the type of different oxides, and they can be listed with respect to their thicknesses too. So for the field oxides, they were mainly for insulation, right? So their thicknesses is somewhere like I don't care level. They are too thick. As we go to the more precious items like the gate oxide, the main building, one of the main building portions of the transistor, their thicknesses are of course getting much thinner, and the quality has to be super well. The good thing about silicon dioxide is, as a native oxide, it already forms on the top without really putting a lot of again, tension on the underlying layer. It just gradually grows by itself. Even in a normal room temperature environment, it does grow. But the other thing is, once you dip into HF, this is a nasty acid, you can selectively remove the silicon dioxide and can be left with the silicon wafer only. So that's a good selectivity with respect to between the silicon dioxide and silicon. HF, I'd like to remind you that is a, as I said, nasty acid. It's not because it's a strong acid, like that's actually counterwise. Most of the time they are kind of diluted, and if you spill if there's a spill somehow, it will be quite difficult for you to notice it if you don't realize it immediately. And it craves for calcium, so it will try to go into your, unfortunately, it will not stop before it finds your bone. So it will continue and start really becoming very painful, but it's also cancerogen, so you need to go to the hospital immediately. All right, the thing that I want to emphasize is, since silicon dioxide is kind of a native oxide of the silicon, it will actually consume the silicon while we're growing it. So you see, if you have this kind of a formation, and if you grow the silicon dioxide on the top, while you're growing the silicon dioxide, you're consuming the silicon underneath. so it doesn't stay at the same level. That's very critical, and we should never forget that we're consuming the silicon in the first place. And this is how their whole tetrahedral bonds and the I would like to say network, but don't take it as like a literally like a crystalline structure. How it looks like, we have the silicon, of course, and we have the oxygen atoms. And once they're bonded, and once they created this very short order range, so there might be some oxygen atoms that can be shared between these tetrahedral networks, like this one here that is shared, and the others might just be non-bridging, so they may not be connecting these consecutive networks. They will be called the non-bridging oxygen atoms, and the ratio of these two will give you an idea about the quality of your oxide. So if your oxide is basically a non-bridging, the majority of it, it will be a lower quality oxide compared to the case when you have a bridging oxides in the majority. Of course, you can have quartz in the crystal structure. That will be a different scenario. I'll be talking about the thermal oxide. This is the situation we have here as the amorphous material. Okay, now we grew our silicon dioxide, we have thermally grown our oxide, and I think you guys already went to the lab to do that. How are we going to understand the thickness? That's the most important thing, the thickness of the oxide. So we have air here, we have the underlying substrate. Believe it or not, even your eye can give you an estimation roughly. You can understand the difference between the two layers if as small as 10 nanometers. So giving you an example, if your oxide was 400 nanometers, and if you grew a little more and made it 410 nanometers, you can kind of start understanding the difference based on the color change of your oxide on the top. So you look at the wafer, and all of a sudden you see, oh, it's not the same color anymore. Okay, it's all thanks to this thickness related light interaction. That's what we call the Fabry-Pérot resonances. That's a detail, but all this light is bouncing back and forth because it's going to be seeing these, what you see, the different refractive indices. Okay, and remember the Snell's law again. It will stay inside, and we will see as the observer, we will see as an accumulated reflection out of this, and that's how we understand the colors. One of these colors will be outweighing the contribution of the other colors that we are observing, because that color, that particular color, when it's reflected, the reflections become constructively interfering with each other rather than destructively interfering. So light as a wave, once it goes out, every time it's going to make you see like a two passage in between the thickness, and that will put the waves either out of phase or in phase as sinusoidal waves. And if they're out of phase, of course, you do not see this color anymore. It all has to do with the thickness here, the D, right? So if that color somehow magically is in phase, so as its reflectance will be emphasized, and then you will be observing that color, and you can see tell the color change as low as 10 nanometers accordingly. But the formal way, as we will cover in the afternoon, is using an ellipsometer. This is our ellipsometer from our tool. I will talk more about it, but there is a laser source here on this end, and there's going to be a photodetector. That's like the generic type ellipsometers. And based on the reflection phenomena here from the laser to the photodetector, we try to understand reflection from the wafer here, the center, the wafer that's sitting in the center. That wafer, based on its characteristics, the thermally grown oxide on it or thermally grown nitride on it, it will alter the properties of the reflected light, and the photodetector will do some reverse engineering to sort out the exact thickness. But you might actually, and there are other ellipsometers, in that case you don't have to do this, but you might have to enter an initial estimate, a guess, as the user. So you put your wafer next to charts like this, and then you try to associate the color that you see coming from the wafer with these charts, the color charts, and then you say, okay, so it might be 0.34 micrometers. So I'm just going to enter that guess and then let the ellipsometer take care. If it is in this vicinity, it will give you the result in angstrom level. So that's as powerful as it is, the ellipsometers. And I would like to remind you, I told you that we could see the changes in as small as 10 nanometers, like here and here. So the change in the thickness is only 10 nanometers, right? And then you can see the color change here pretty nicely, abruptly, from the violet blue to blue. This chart is for okay. All right. So there are other ways to characterize the silicon dioxide. We just looked into the non-destructive optical way, but there's of course an electrical way too. In that case, you have to create the same configuration that we worked on before. Metal, you need to have a metal, an electrode. It could be polycrystalline silicon too, but underneath that, you can put your oxide, the thermally grown oxide, and we have the semiconductor. Again, what did it make? Again, it's the same MOS structure, metal oxide semiconductor structure. You try to drive this oxide by applying voltage from the top, from the gate side, okay? Since this oxide is very thin, and I would like to remind you the electric field is equal to, actually, I won't write the derivative form, but I will say simply voltage across this whole oxide over the thickness of the oxide. Let's call it T. Of course, since these thicknesses are in terms of nanometers or so, the electric field that you will build up will be really large, even as low as you apply like a few volts here, okay? And we can characterize these silicon dioxides. We know that they will break down around these values, 10, 12 megavolts per centimeter as the electric field, as the created electric field. What does that mean? Well, under the influence of that electric field, the electrons can actually conduct and can jump from this side to the other side, and we will start seeing a current as if we don't have an insulator here, okay? That tells us the quality of our oxide. Well, if we have defects here, they already get broken before even reaching that kind of an electric field. So those are going to be the defective oxides. Yeah, you can also try to estimate the thickness based on running the current again in another electronic measurement characterization. You try to run the current, and there will be accumulation in the silicon dioxide, and after a while, based on the thickness, there's going to be another breakdown here, and the oxide will start to conduct. So you can start to try to estimate based on the time that's needed here. You can try to estimate the oxide thickness likewise. But the best way is, of course, doing the characterizing the capacitance, the oxide based on the capacitance measurements, the capacitance voltage measurements. So we already looked at that yesterday. I'll just very quickly remind you that we used this another NanoHub software. This time we used MOSCAP here. I think Abacus has also something similar inside. So You don't have to follow me for this example because I'm going to do it very quickly just to remind you, but you can just search for MOSCAP and then NanoHub, and then you will end up with this, hopefully. So this is showing you another simple configuration. We have the insulator that we're trying to characterize. So these are gate oxides and thin oxides. They're very thin. Look at the sizes. It's at this point it's even thick here. It's like relatively thick. It's 100 nanometers. Actually, those gate oxides are supposed to be much thinner. Anyway, so we have this oxide, the gate oxide here. That's the fundamental building block of a MOSFET, the transistor, which is the fundamental building block of our all computational sources, right? So we have to make sure that these capacitances, I'm always saying capacitance, but these oxides are all nicely characterized, well, optically and electrically, so that they will work wonderfully when we build transistors out of them. Okay, so let's look at it. We have the semiconductor that's doped 10 to the 15, and it's a p-type dopant. Okay, we actually examined this configuration before. There will be banding like we examined before, and then we get the gate electrode as an N plus polysilicon, and we are looking into silicon dioxide. How do I know that? Well, the dielectric constant is given by experience. I know that that's the silicon dioxide. And I don't think I have to change anything here. So we're kind of sweeping from a negative voltage, okay, from the metal to the ground, where I apply the ground to the semiconductor, minus 3 to 5 volts. And let's look at the response. We have an AC voltage also associated. Yeah. So this is a very important graph that you're observing here. It's the capacitance versus voltage graph. Let me remind you very quickly that we had the gate, the oxide, and the large semiconductor layer here. Well, what happened was we were applying negative voltages to the gate side first, and this was our oxide. That's our semiconductor. It's p-type, so it's rich with holes. So once we apply the negative voltage, all of the holes would try to go there, attracted under the force. And what will happen? Well, it's already a p site, and this portion would be even richer. So we would have a p plus kind of region here, and that would be what we will call the accumulation. The names are not super critical, but what will happen in the end is if I were to measure a capacitance here, the capacitance would totally come from the oxides. And you know how the capacitance is found. It's epsilon times area over D. If you do not remember the simple formula, let me remind you that's the D, that is the thickness. Area is, if you think about it in 3D, of course, we have the area here, right? That's that area. And epsilon is the dielectric permittivity. In this case, it's a silicon dioxide. So that's basically the dielectric permittivity of the silicon dioxide times the dielectric permittivity of free space. Anyways, those are details, but this is the capacitance that I would say. Now, let's do something differently. We had the gate voltage, we had the oxide, we had the silicon here, again, P. Now we applied plus, okay? In that case, what will the plus attract? They will start attracting, even though this is supposed to be a P site, they will start attracting the electrons here. But I have holes here too, so let's show it the holes with different color. So what will happen? Well, these kind of will charge neutral ways. They will try to annihilate each other in a way, and then they will create another layer that is almost free of, in total, free of charges. So that would be the depletion category. So what will happen if it's going into this kind of a case when we apply plus voltage? Well, it will act as if I have two capacitances here. Like I have a capacitance coming from the oxide, but I also have a capacitance coming from the underlying depletion region, and that would be the series combination of the two. And what will happen if you combine two capacitances in series? Its value will drop. So let's start. Negative, it's going to drop. And then if I increase the positive voltage here, it will attract so many electrons, so it will not be a depletion region anymore. It will become a negative polarity region due to the electrons. So that's what we call the inverted region. And the capacitance value will go back to its original, because then I will be left with only one capacitance here. So looking into this can give us a lot of information about the quality based on the defects, based on the charges that are accumulated inside this oxide. Okay, this gives us a chance to take like an X-ray of the whole oxide. These values will be shifted and everything will be different. And the reason is, again, this is the main building block of the MOSFET, or these kind of field effect transistors, and would like to characterize them nicely. So going back to the other screen. Okay, so this is our furnace that you're seeing right now, and then we feed in the furnace. I'm sure you have done the similar thing. With two main gas, there could be more. With nitrogen and oxygen, they just flow in, and we load the furnace with these kind of wafers. It's heated up right now, that's why it's glowing. And we have 3 zones of our furnace. That means that once we load the samples into the furnace, the furnace tube will be heated by these 3 zone centers. 1, 2, 3. 3 heaters. The main idea is to keep the furnace almost at the same constant temperature as much as possible, because this oxidation will be very much closely related to the temperature, okay? So the oxide that we're growing is extremely sensitive to the temperature. And we have different ways of growing the oxide. I will talk about the first two. We can either flow in oxygen gas only, or we could flow in water vapor. The water vapor will make this be called wet oxidation, and just the oxygen as used as the oxidant, that's the key word, we call that to be the dry oxidation. And we would use these kind of parallel lines, not just a simple furnace like I shown you, to grow tens of, if not hundreds of wafers with thermally grown oxide at the same time. The idea is to make sure that these two reactions takes place. The wet oxides are lower quality. So if you ask yourself which one has more bridging oxides, which one is a higher quality oxide, of course the dry oxidation will give you a higher quality oxide. It will take much longer to grow it in compared to wet oxides, but the quality will be much better too. So this whole oxidation process has been formulated by Grow. Del Grow. That's the reason why it's shown like that. He was only a graduate student, as far as I know, when he built this oxidation model, and the model goes on like this. So let's remind ourselves. So first we have the furnace and our tube, and the wafers are sitting inside, and we flow in our gas. Let's say this is oxygen right now, and we heat up the chamber with the zones. So the oxidant, which is the oxygen here, it will have a certain concentration. and it will have higher concentration, and it will go down to the lower concentration. We know what this is. This is just the diffusion process. Diffusion of the oxidant of the gas. So it will go down to the surface of the silicon dioxide, but that's the key thing. It will not stop there, okay? It will go into the layer, and it will penetrate. So there's going to be an absorption process here taking place at the interface, okay? So not all of the oxidants, not all of the concentration will be able to penetrate. So that's why CS is not the same as C0, that is the one that's inside the silicon dioxide. Well, it will be higher than C0. Let's say 90% of it made it, but it's still going to be different. Later on in this model, there's going to be another diffusion. Of course, it has all these mathematical accompanying equations. I'm not bothering you with all of that, but we have high concentration here. We have to go down to the lower concentration. That's when it stops at the interface. So shortly, the oxidant should go through all these steps, should go down to the silicon layer to start the chemistry. As the fourth step, it goes down there and it reaches this concentration, and it starts breaking the silicon bonds. What does it do? It replaces them with oxygen. Okay, and then that's how the silicon dioxide is grown, from bottom to the up. All right. So that's showing you the two ways the silicon dioxide reacting with oxygen and water vapor. We'll examine these things, the growth rates. So I'm skipping that shortly, but again, emphasizing this in this very simple examination. Let's say that we originally had the silicon wafer level to be like this at this point. And then we totally grow an oxide of TOX, that much, okay? The level, since we are consuming the silicon dioxide, will drop. The new silicon wafer level will be much lower. So let's call this the consumed silicon, T silicon, that portion. Now let's look at our chemical reaction. That says that if you use 1 mole of silicon, you will end up with 1 mole of silicon dioxide. Now, let's try to see how many moles we have used for silicon and silicon dioxide, how many moles have we created. If I multiply T oxide, the thickness, times the area, which area? This area here. And that's going to give me the volume. If I multiply with that with the density of silicon dioxide, that's going to give me the volume times density, the total mass that has been created right now. And if I divide that by the molecular weight of the silicon dioxide, that's going to give me the how many moles that I have produced at the end of this reaction. I just need to equate that, like you can see here. I won't write it again, to the consumed silicon. Right now, the volume will be T silicon times A times the density will give you the weight of the silicon that's been consumed, divided by the atomic number of atomic weight of the silicon, and then you end up with the ratio here, the T silicon over T oxide, right? And that's going to be 0.45. So that means that if I build 1 unit of silicon dioxide, it will be like an earthquake. I will collapse 0.45 units of silicon on down to the bottom level, lower level. So that's why I asked this very simple question to my graduate students here, and it's very unfortunately it's only a few can solve this very simple problem. I tell them, can you show me the new pattern that we will get if we grow a thin layer of oxide, a thermally grown oxide, let's say 100 nanometer on the top? The numbers are not critical, but mostly they just draw this all equal and dull. That's not the answer, right? Because remember, we will consume the silicon underneath. That's one thing to remember. So let's look at this part here. If we start with this silicon level, it will get lowered down. 45% will be here. I will grow 55 at the top. Okay, that's good for that portion. How about the others? Now, the second important thing that we need to remember is the oxidants, let's say oxygen in this case, will have to diffuse through the all oxide here. So that makes this process on the sidewalls to be slower than the process here, because here it just sees the bare silicon and it can grow the oxide much quicker. So this is quick. So what I'm trying to say is the total thickness that I will grow will be thicker here compared to the total thickness that I will grow on the other portions. So meaning that I will not be able to eat away that much of silicon here. So it's going to be higher. So you see, the levels are not going to be the same. So it's going to be a little higher. And if I'm consuming this much, I couldn't draw it well, but if I consume this much, I should also have more grown on the top too, right? 45%. And then I can just that's the tricky part actually. That's some part that I don't really pay too much attention. The sidewalls are also critical, but I don't pay that much attention to the sidewalls. The importance is here the flat portions, the horizontal portions. So that would be the answer. I want you to understand that first, we are consuming the silicon. The second is it's gonna be different. The oxidation rates will be different if you already have silicon dioxide. So this is showing you the recipe of an oxidation process, a standard oxidation process. I'm sure you've gone through a similar examination. What you do is, well, you start with a temperature. It could be even as low as room temperature, and then you gradually pull it up, and then you stabilize it. That's where the oxidation takes place, and then you ramp it down. So you lower down the temperature, and then you cool it down so you can take out the samples. If you do not wait for the cool down or the ramp up, first you can harm the tool because it can't catch up the speed. Secondly, and maybe more importantly, you can build up a lot of thermal stress on your wafer. So all these wafers, once they are taken out from, let's say, 100,000, not 100,000, 1,000 degrees to outside room temperature, 25 degrees, there's going to be too much of a sudden abrupt change in temperature, and it may build up unequivalent amount of stress on certain points, and it may just break the whole wafer. Okay, so these are now the three gas that we can pull into the chamber. The recipe says that you're pushing nitrogen first. This is going to be actually helping you to kill the, let's say you're trying to grow a gate oxide. There's going to be non-idealities inside your gate oxide. Those non-idealities will be neutralized with the flow in nitrogen. It will help with the formation of the silicon dioxide in a much more better way, if you like to put it that way, in the long run. But also it will keep the oxide, it's an inert gas, it will say that, okay, don't start oxidation as of yet. So you see, these are the minutes we're ramping up, and this is where the growth of the oxide takes place. And that's why we flow in the oxygen, and we somehow flow in the HCl gas too. That's something we will be talking about as well. Okay, so the oxidation rates and the oxide thicknesses will be depending on the temperature. So these are several different temperatures on the graph that you can see, and this is the time axis. This is time, and this is the oxide thickness. in terms of micrometers. So if you operate at different temperatures, I told you it's all chemistry dependent. So chemistry dependent means it's going to be temperature dependent too. Let's say you put the wafers in the furnace for 1 hour. Let's look at the output result at the end of the 1 hour. You always increase the oxide that you grow by elevating the temperature. So the higher the temperature, the quicker the oxide will be grown. And in a similar fashion, there's going to be a dependency on the crystallography of the wafer too. So since we're starting with a wafer, it's going to be critical, and it has to do with the kinetics and also the chemistry, right? So it will be very much, again, depending on how many bonds I have available on the top surface of the silicon wafer, because the oxidant will come in here. If there's too many bonds available, the oxidation rate will be quicker. I hope you can visualize it in your mind. If I don't have that many bonds, it's going to be slower. And this was the diamond structure of the silicon crystal. It will depend based on how we orient the surface, like either in the 111 I might have more uncompensated, what we call dangling bonds, or less dangling bonds on the surface. Okay, can you hear me? So it says the connection may not be stable for a second. I hope you could hear me. But let me remind you again. So everything will depend on the number of the available bonds that you have on your wafer surface. Okay? So if you have more of these bonds available for you, these dangling bonds, it will be easier for you to grow the quicker to grow the oxide too. Can you guys hear me? Can you give me a thumbs up? Okay, good. All right, for the 111 symmetry, we have more bonds available, and that's going to increase the rate. So let's look at it. Let's take the same temperature, same time, like 1 hour, 1000 degrees, 1 hour, 1000 degrees. So it's here. This guy is here. The other guy is a bowl. So I don't know if I can draw it well, but it's like here, as you can see. The other guy is here. So 111 will deposit or grow much quicker for that reason. And also it will depend on the dopant concentration. While we're implanting these dopants, there's going to be tremendous amount of crystal defects created. So oxidation will make use of those defects and will make sure that it will oxidize this area much thicker. So oxidation will be much more easier in that area, and it will be thicker relatively compared to these sides. Okay, one thing before we do the MATLAB, we also flow in the HCl, if you remember. So people were really worried that their transistors were not functioning properly in the old days, like in 1960s, 70s even. They weren't sure what the cause was. The cause was these kind of mobile ions that can be introduced from anywhere. Like if you work with a beaker in your lab, you end up with these, you can't avoid these kind of mobile charges. Once they enter into your oxide, like this sodium, potassium, they will be under the influence of the electric field. They'll just propagate. And let's say your device might work for a while, but it may really alter the whole performance of your device after a few hours or so. To neutralize them or to make them immobile so that they won't be under the influence of an electric field, they won't be moving around that much, we put in a very reactive gas, and we put in HCl. That will neutralize those mobile charges and minimize their influence. But on top of it, we have lots of other non-idealities, like there might be some still silicon bonds that weren't oxidized there. So they will create these interface charges. There might be incomplete oxidation of the silicon. Okay, they will create more charges for you, or some of those silicon oxygen bonds might be broken inside the oxide, and they will also create some non-idealities. The whole issue is like an architectural issue. You're trying to build an amorphous layer on a crystalline structure. So as you can see, some of the dangling bonds will not be compensated, so they will bring you these interface charges. That's going to be a recombination side. If we're talking about the diode performance, that's going to be a defect portion for our oxide. Okay, so if we look into it, we will have also incomplete oxidation, like the silicon is not oxidized. So that's going to create our the fixed charges inside the lattice. So it's hard, but it's still very nicely working mechanism that we can still build an inherent oxide out of this too. All right, so that is where the especially the capacitance voltage measurements come into play, because we try to characterize the amount of these non-idealities inside the oxide. Okay, now you have built your oxide, your MOSFET, and you're still trying to shrink down the sizes. While you're shrinking down the sizes, this oxide thickness also will be brought down to a thinner value, like 1.2. But as you're doing that, it's becoming too thin, and the electrons can really punch through that thickness. So you have to change that silicon dioxide. You're not satisfied with silicon dioxide anymore. You change that with what we call high K dielectrics to put a little barrier for the electrons, and these high K dielectrics will withstand these electric fields and will stop the electron conduction from the gate down to the silicon. If you stop that, you will also prevent the leakage of the current too. The current won't be leaked away, so you consume less and less power. Hafnium oxide is one of those type of oxides, unlike the silicon dioxide, so it doesn't allow the leakage current to be occurring. Okay, so at the end of our lab, what we do with our students is we looked at these wafers and we record their the end results using the ellipsometer. I'm sure you guys will do a similar experiment in the afternoon. So we looked at the orientation, crystal orientation, and also depending on whether they had an initial oxide or not, what the oxide will be, the end of the oxide thickness will be. You see 111 gave us a much thicker, this is all in angstrom, so it's like 178 nanometers, as you can see. Comparatively, the 100 with less of those bonds available brought us like a 0.14 micrometer. And when we have an initial oxide, there's going to be a difference, of course, at the end. So let's try to understand what kind of a difference we're talking about by looking into these simulations. Okay, so I assume that you guys have, let me share the other screen. I assume you guys have the little MATLAB code that I provided. Okay, so it's going to be called oxidation.m. So this is the MATLAB environment, and the current folder, the files will be shown here. This is where the variables will be loaded once we run our codes. This is the command window where we can immediately access MATLAB and run some commands over the MATLAB. So if you double click on the oxidation, all you need to do is just run the code from this run button here, and then it's going to ask you a couple of variables like enter number A. So we will, and this is our Canvas webpage. I hope you guys are entering this webpage and checking it regularly. So I did put 2 virtual labs for you, but of course this is not homework. By the way, I'd like to remind you, these are As of now, graduate level, they're graduate level virtual labs. So I just put them there so you can go in like this and watch some videos showing you how we operate the oxidation furnace in our clean room here. This shows you step by step the how we load the samples, how we run the recipes, how we use the ellipsometer. So it's taking a while to load them, so I won't wait, but let's come down. Yeah, these are the A, B, and tau parameters. So these are the critical parameters that I will enter. They all come from the Delgro model. Okay, so what parameter are we going to use? We're going to use these three parameters, 0.23 and goes on like that. I use the same, so it will be in the memory of MATLAB. It's the first one is 0.232. The second parameter I will enter is 0.0, what was it? Yeah, 1. So if I look at the memory again, 0.0104, and the last is 0.6, I believe, 0.6. Yes. Okay. So I hope you're with me at this point. So what we will do is enter the initial oxide thickness. The first initial oxide thickness. I will say that we start with only 1 nanometer of a thickness. So what we're trying to compare is the two case. Let me also put it here. So we're going to try to understand the oxidation rate of two wafers, wafer 1 and wafer 2. Okay. So on wafer 1, I have a native oxide that is only 1 nanometer. And I will, let's type that in. I will keep them in the furnace for 4 hours, both of them. So I hope you also got a similar graph like this once you entered the initial oxide thickness. It should pop up. Okay, so at this point, I'm going to use this data cursor. This is the data cursor. I'm going to choose that. And I will come down to the plot, and I will just click on the plot at some point, and then it will bring me the points, the data points. So I will go with the arrows on my keyboard to find 4 hours, because that's where I would like to go to. Okay. So at the end of the 4th hour, what do I see? I see that an oxide is formed and its thickness is 0.12 micrometers. Let's round it. So let's round it, and it's going to be 0.12 micrometers. That's the thickness of the oxide. Now, as for the second wafer, let's run the code again. So I'm going back to the same oxidation.m, just canceling that previous graph and running the code one more time. And I will enter the same numbers, 0.2, 0. So if you just click on the arrows on your keyboard, they will come back from the memory. So 0.01 something, so that will come 0.6. Yeah. And then this time I will enter an oxide there. So I will say I already have an 100 nanometer oxide. So let's draw it. I also have a 100 nanometer initially here, or 0.1 micrometer. Okay, hitting enter, and then I end up with this. Okay, are we all on the same page? No? So I just simply run this code for 2 times, and again, I'll do the same. So I'll use this data cursor and I will put it on the graph and try to find out the point 4. So I read the number there. So it tells me that now at the end of the 4th hour, the total oxide thickness has become 181 nanometer. So that means I grew an additional oxide of 81 nanometers. Okay, I know it's not super visible there, but let me repeat the results. In the first case, for the first wafer, I had a native oxide, and I grew 0.12 micrometers on this 100 plane for 4 hours. And in the second case, for the wafer 2, I had an initial 100 nanometer oxide, so I was only able to grow 0.081 micrometers on the same 100 for 4 hours. So, why did we grow less? Actually, we already discussed this. We grew less because the oxidant coming from the top, okay, was having a difficulty to penetrate the whole thickness here. So it's going to grow less at a slower rate. So that's why if you have an initial oxide, the end result will be different, and it's not a linear system. That's what I want to emphasize. It's a nonlinear output. Okay, now let's close it again. We will run it for the last time. I will do a third wafer, wafer 3, with another native oxide of 1 nanometer. But this time it's going to be a 111 wafer. Okay, so let's run the code. It's going to ask us the AB and tau parameters. I will let you know the AB parameters. So A is 0.138. So let's enter 0.138. And B is the same. So if you write 0, it's going to come up. And the tau is 0.391. So 0.391. These three parameters. And then it's going to ask us the initial oxide. I will again enter the native oxide of 10 angstroms, meaning 1 nanometers. And at the end of the 4th hour, let's see. What do we expect? We expect a thicker film. Again, doing the same, going to the data cursor, going to the plot, putting it on the plot. I somehow magically put it right at the bullseye for, so it gave me the result. How much did I grow? 0.1466 micrometers. What's the difference? Now this is 111 plane, again for 4 hours. So we understand that the initial oxide is the worst. 100 oxide, 100 initial oxide is the worst. 100 no oxide is somewhat in between, but 111 oxide is the fastest without the initial oxide. Okay, I hope you will also measure the ellipsometer measurements, and then you can use this code and estimate how much you were expecting. But of course, I would like to remind you that these AB and tau parameters may not exactly match your furnace modeling. So over there at Norfolk, okay, so it might be a little different. But I'm expecting not so different results to come up as well. Okay, so that kind of concludes the thermal oxidation. Let's quickly visit the ion implantation. And in the afternoon, we'll do more deposition. So, starting from the hydrogen atom and the quantum mechanics, we've done a lot of things in these 2-3 days. And we'll continue to show you more ways to actually do manufacturing. Okay, so let me share this other screen. We've been talking about the dopants. The dopants will be helping us to dope the sites. We will have electrons as the majority, or holes as the majority. All these creation of the PN, and then we created the PN junctions once we put them together. Then we obtained the solar cells thanks to the PN junctions and their the selectivity between these two, the holes and the electrons immediately. And then we went into the oxidation. We looked into a little bit of evaporation. We'll talk more about it in the afternoon. We talked a lot about MOSFETs too, the MOS capacitance. So now, going to the ion implantation. Yeah, I gave you these as homework. If you remember the MOSFET, how we create the MOSFET, just read these comments here and try to follow all these patterning methods, all these new process methods. Okay, so the ion implantation. So we talked about a different way of introducing ions. These would be the dopants. The first immediate way was the diffusion, if you remember. We could diffuse them into the substrate, and we could dope the silicon that way. But look at the example. It's not really well controllable. Fusion is not so controllable, so it will also go underneath the mask too. In contrast, people have come up with the ion implantation. So their idea is to drive these ions to a certain level of energy and then implant the ions with these high energies into the crystal, silicon crystal. But of course, it will create a lot of these damages on the crystal, so you have to repair those damages too. So these are the advantages and disadvantages. Of course, it's a very expensive tool compared to the simple diffusion process that we covered maybe 2 days ago. But it's a very fast process, and it's also a low temperature process too. We don't have to increase the temperature. That increasing the temperature, you should always keep in mind that there will be thermal expansion going on all the time between your layers. So there should be more and more stress build up. If you have like several cascaded layers, temperature increment increasing can be critical. Also keep in mind that you might have polymers in your case, like you will see next week, like photoresist. They will be very susceptible to temperature deviations, and they can't really survive after 200 Celsius or so. So all those are going to be critical. Okay, now how do we do the ion implantation in the first place? We need an ion source. Well, to create an ion source, we have a filament. That filament will provide the electrons, and then there's going to be a gas that's going to be available for us here. And that gas, let's call it AB, a gas of AB, will be ionized by colliding with these electrons, and then we will create the ions that we want, and the ions that we produce will be guided in a very clever way thanks to these magnets, because charged particles can be guided with the external magnetic force. We'll cover that in a bit. And then we will speed them up to high speeds, and we will make sure that they will find their position on the wafer surface. We will scan the wafer surface with some electrostatic plates. We will trap some neutral particles. If there's still some neutral particles here, we don't want to dope them on our wafer, of course, as foreign particles. We will capture them here along the way. So all these electrostatic ion optics, that's what we call it, will enable us to guide the ions to filter out the neutral particles and to nicely make sure that they will go to the selected portion of the wafer. Okay, so this is another look of how we actually accelerate them. It's just like a Formula One race. You speed up the car and then you just make sure that it goes to the position after turning all these bends. But during the creation of the ion, you might end up with lots of different variants of the ion. So you might end up with like these kind of scenarios. Even you can ionize, let's say you flow in some boron fluorine combination of a gas. You might ionize the gas in different ways. All these are possible. But actually, this is what you would like to use, right? So what you need to do is, with the help of the magnets that you have, the magnetic fields, you can guide the charged particle to the correct selected aperture. And this way, using the magnet as a mass spectrometer, you will make sure that the correct radius, the correct trajectory of the following ion with the correct mass will be going through. And the other ones, the heavier ones, what heavier? Heavier, its mass will increase. See, in this simple equation, it's the Lorentz force equating to the centrifugal forces, if you're familiar. If not, that's not too critical, but what's happening is the R, if you take it out to the other point, is proportional to the mass. So the radius, the trajectory can be predicted. And you can filter out these heavier ions. You can make sure that they won't go and infiltrate into your silicon surface. When they interact with the surface, these ions, they will be stopped. How? By basically colliding with these kind of silicon atoms all together, or they can go into interactions with the electron clouds of these silicon atoms. This is what we call, if they crash into the silicon and if they displace the silicon atom, this stopping will be the nuclear stopping. Otherwise, it's going to be called the electronic stopping, and it will create heat, of course. The other one, on the other hand, will damage the crystal silicon. So we're now observing two situations, A and B. In the A case, the ion that's emerging into the silicon crystal has covered a long trajectory. The reason is it's a light ion. So a light ion and a heavy ion is compared. Let's say that they have initially the same non-relativistic, same energy. So I'm saying non-relativistic, meaning that I'm just showing their energy with the simple kinetic energy formula, 1 over mv squared. Okay, so since their mass is different, so let's say this is m2, this is m1, okay? The velocity of the boron ion will be higher than the velocity of the same energy arsenic, right? Since the velocity is large, while it's passing through the crystal structure, it will not have enough time to actually interact with the silicon. So it will just not be scattered too much. Instead, it will continue its trajectory right along, just like a bullet. And it will start losing its energy or speed, I should say, and then it will start colliding because it will start interacting. It will go into these and reacts just like an electron. It will start seeing all these potentials applied on it. So it will start hitting the silicons more and more frequently, and it will damage the crystal there. As for the arsenic, it already starting point doesn't have that kind of a velocity, and it will start interrupting the crystal structure already initially. I'll show you, I hope the time will permit, and I'll show you in SRIM the simulation tool that we use. But arsenic is now penetrating in, as you can see, and it's dislocating the silicon atom. We have seen these defects. We didn't see in ion implantation, but we have seen these defects getting formed. These were the interstitial silicon atoms that were created. and we had, if these were stopped, the arsenic was stopped, that would be a foreigner defect, point defect structure in the crystal lattice. Okay, all these can be nicely modeled with what we call Monte Carlo simulations. They are depending on random motion of these kind of scattering mechanisms. But instead of running, as you will see, lengthy simulations, we can just use and fit them to simple Gaussians, okay? Like in this formula. The formula itself is not important, but the important thing is all these ions will have a similar Gaussian distribution to your grades when you take an examination. It's very funny to also see that. Why? Because Gaussian distribution makes sure that if you end up with a Gaussian distribution at the end, it will make sure that it's really a random process that's happening. You're not under the influence of a selected region, but it's all like happening irrespective, or the whole interaction is happening at the same forces, under the influence of same forces all around across the crystal. Okay, so like I said, depending on the mass, like we're seeing here, boron, phosphorus, and arsenic, at the same energy, when you have the same energy, arsenic will penetrate the least, whereas boron will penetrate the most. Why is it critical? Because you will have to work with these kind of masks. Like in this case, it's a photoresist. It's not the super good way of doing it because it's a polymer, but if you ion implant from the top, and if your boron is as the lightweight, it can penetrate all the way down, then that defeats the purpose. So you need to make sure and design your photoresist thickness thick enough to actually stop these ions penetrating all the way to the bottom. But that is still not good enough, because you can end up with these kind of scenarios when you shoot your ion into your crystal, and it might just occur that, see, if you look at the crystal from a certain angle, you might just see through the whole crystal. You don't see any silicon atoms across. So this ion can just penetrate through, whereas this ion will be with a slight different incident angle, let's say theta, will bounce back. Okay, so this also gives us an idea how to circumvent this problem, but let's see first the problem itself. So I told you that this would follow the simple Gaussian distribution originally, but if you happen to see those kind of channels, okay, those kind of loopholes, so the ion will penetrate more and the concentration will really go into the depths. How can you circumvent that? One way is to send the ions with an angle, just like the case here. Send with an angle, and then you see that it's gonna strike those crystals, the silicons in the crystal. Yes, but then that will make sure that this portion will be shadowed. Well, how are you gonna counteract that? Well, you can send the ions also at the other angle too, plus minus 7 degrees. So you can make sure that these portions will be shadowed at the same, around the same amount, but still it will receive some ion implantation here too. One other way is to actually make the crystal defectful, or you need to make the crystal amorphous. You need to change it to an amorphous crystal, or you can get an amorphous crystal, amorphous material in the first place, like oxide, and do the ion implantation there. Not too thick, okay? If it's too thick, then it will mask it. But if it's not too thick, this will make sure that this amorphous material will make sure that we have definitely will go through some scattering. So it will prohibit the channeling likelihood a lot. Or, as I was saying, you need to maybe here, yeah, people apply a certain dose and they try to understand, like with different ions, like you can see here, how much of a dose is needed at what temperature to actually make the surface amorphous intentionally, so that this channeling will be minimal. Okay, so like in this animation, we're seeing the propagation of the arsenic in the crystal. We are creating these self-interstitials, and we're also creating the vacancy defects. And at some point, the arsenic will stop, so that's going to be bringing another zero-dimensional defect too. In this picture, this is another one of those MOSFETs, or another pattern maybe. We see that here at the end of the ion implantation, okay, I can clearly see that it's no longer a crystalline structure. Why? Because all that damage, end of range damage, that's what we call it, amorphized made it amorphous. That portion of the lattice became amorphous. So people have to come up with some damage engineering methods. How can we repair the this damage? Well, the best way is, again, make use of the diffusion, right? That's what we've seen. How the carriers wander around with the help of diffusion, but also likewise, these kind of atoms they can also find their locations by heating up the or annealing, I should say, the defectful crystal now. And these are the recipes. So we carry out these with these kind of high power laser or electron beam, high intensity halogen lamp, okay, in this kind of an RTP. This is a cartoon that I just put because, believe it or not, we lost our RTP or RTA, rapid thermal annealing tool. We're missing a couple of things here. In terms of the tool, the maintenance needed to be taken place, and we send it to a source in California, and all of a sudden we couldn't find it again. So that's why that's a kind of an inside joke. But the important thing is we have to increase the temperature tremendously, very, very quickly. That's where the meaning of rapidness comes from. We need to increase it 200 Celsius per second, and we need to cool it as well quickly. So it's not going to be a long, like, oxidation furnace kind of a thing. So this will hopefully repair your damaged crystal. Now, in this last 20 minutes or so, I would like to show you a couple of things about the SRAM. So, of course, we will not be able to incorporate that with the MATLAB, but at least hopefully you can follow me. So what I'm doing is I'm calling the SRAM, so you can do the same. Just like any other Windows application, I'm typing SRAM, and then it pops up, and then I am clicking on it, and this will bring me this screen, hopefully, for you guys too. Okay. So we would like to see the demonstration of the light ion and the heavy ion, right? So let's do that because we don't have the time to carry out the whole computation. So let's just go to the trim calculation. I am using 2 monitors, that's why it's immediately disappearing. Now here, we will do 2. So first one, the first ion that we will send is going to be boron. So come here to that says PT. That's the ion data. The bottom part will be the target data. So click on PT and choose boron. That's going to be our acceptor dopant. Choose PT. Okay, for the energy that we're going to send it, 10 kilo electron volts is very low. So let's make it like, I don't know, 100 kilo electron volts. That might still be low.
Would you be able to oh no, it's not. Not good. Would you be able to start over?
Okay, sure, of course. So what I just did was I come here and just like any other Windows application, I type SRIM, SRIM, and this should pop up on your screen. This menu should pop up. That's it. That's where we are. And then I clicked on the trim calculation. Okay, so that's where I am. So not the SRIM part, but the trim part. Okay. And here I choose this portion is the ion data. This portion is the target data. So I choose my boron ion on the periodic table. My acceptor says atomic number 5. Great. Mass is 11. Its energy needs to be increased. 10 kiloelectron volts is pretty low. So increase that to 100. But I don't want it to go to too deep either. So we'll see. I don't know by heart. But remember, we talked about the angle of incidence. So we can send the ion at a certain angle too. But we'll just not do it, okay? So if you do that, the channeling will be less and less. But we will not go into that discussion. Yeah, I mean, calculation. Not the discussion, but calculation. We will only have one layer because we only have 15 minutes left. So one layer will be good enough, and that layer will be silicon, of course. So click that little PT thing again, and then choose silicon as your target material. And it will bring up the atomic number, the weight, and all the other things. I'm not going to go into those, but okay. Now, if you're with me, now we're almost there. There's one thing here. Decrease this total number of ions from this crazy number to, say, 100. Okay? Because otherwise it will send that many, 99,000 times those ions. Of course, that's going to be a much reliable result because we won't have only a few ions, but we're going to be good for that. And here, let's think about this. So the width of the layer, that is going to be the thickness of the layer, the silicon that we're going to examine. So this is in terms of angstroms. So in terms of nanometers, it is 1,000 nanometer. Yeah, it's only 1 micrometer thick right now. And I just hoping that it will be good enough for us to visualize. It may not be, so we may have to run it again. But if you're with me, just let's say save input and run trim. So once you click that, it should gradually send all of the ions. 100 should be completed. And on your screen, you should see the this calculated trajectory of the ions. Oops, I lost it because, so that's the thing. If you make it smaller or bigger, you kind of lose the thing. But it's not critical at this point. Let me click on this ion distribution. That's going to show us, hopefully, yeah. That's going to show us where the ions are. So I'm taking just across this x equals 0 or y equals 0, I should say. Let's say that this is x and this is y. I'm just taking a snapshot across y equals 0 portion. And this is what I'm saying. I hope this is kind of reminding you something. With only 100 ions, we were able to observe some sort of a Gaussian distribution up to some extent. And they stopped like around here. And the location, so that's already giving us the straggle too. But see, that is 1 micrometer. The complete thing is 1 micrometer. So that should be like 500 nanometers, right? So this is more like a 300. So that's almost similar to the range here. So they kind of stopped around 300 nanometers. Okay, so let's try something because I don't want to lose this. Let's initiate another SRAM. Okay, so going down to Windows and writing SRAM one more time. I don't know if it will allow me to do that, but I don't want to lose the screen. Okay, it did. Nice. So it brought me another one. I will click on the trim calculation. Trim. And I will do the same things that I did for this time phosphorus, or maybe just to see the importance. So I'm gonna still be on the 5, this same group, okay? But I'm gonna choose arsenic this time. Yes, ions have been changed to arsenic. Give the same energy, 100 kiloelectron volts, because we want to make a fair comparison. And we will leave this again to be 1 micrometers, but now the target is also silicon. And remember, we have to change this total number of ions to 100 again. Yeah. So now we're ready to run this too. Save and run it. So it's running on my screen. Yeah, it's very tiny, right? So we know the reason, because it is a heavier ion, so it will be stopped a lot more earlier because it's going through nuclear stopping rather than electronic stopping. It's not interacting with the electron cloud, but it's interacting with the crystal itself. So if we look at the ion distribution, now remember this was the other graph, so let's bring it. So if we draw it for this one, this is also similarly looking to the Gaussian, and its range is much smaller. It's also shown here, more or less around, because that's like a Gaussian fit too. That's the midpoint of the Gaussian, like around 70 nanometers only. Yeah. So the heavier one got stopped earlier. Let me see if I can. Okay, ion. Okay, we did not include that probably. Let me see if I can do that. Full damage cascade. So I'm just changing this to full damage cascades just to see something if I can. I'm not sure. And it's still the arsenic, 100 ions, and running it. Yeah, yes, now it is showing us not just the arsenic, hopefully. Yeah.
Do you want us to change it as well?
Yeah. Or you can just follow my screen too, doesn't matter. But I want you to see one thing. It's not just showing us the arsenic, but it's showing us the damage that it's creating inside the crystal too. These green ones are now the interstitial. They're the knocked off silicon atoms from the crystal. Okay, so wherever the arsenic is going, of course, it's taking a little longer. So let's try to see the same thing with, if we can, maybe, is it the same simulation or? Yeah. So the boron, I'm gonna try to repeat that for boron. Yes, so this is the drastic importance. What is so different between the two? Let me. Okay, I hope you guys can see the difference clearly. Boron is only giving us the damage towards the end of its range, towards the stopping point. When it loses energy, then it starts to interact with the crystal all of a sudden. But arsenic is already like when it starts already has low energy, low, not energy, but low speed. So it starts to knock off already these atoms, from their locations. Okay, so let me show you the end result. I mean, on both days, unfortunately, we couldn't go to that part, but what we were aiming was to show you and to compare. So we get these plots, that's good, we've done this, but we were gonna also show you the way to repeat this on MATLAB too. Just gonna show you the result, the end result. If this thing allows me. Once you fit them, like I gave you the clue, once you fit them with the Gaussian, okay, I'm hoping this is gonna come up at some point. Yeah, they're gonna be really nicely matching to each other. So okay. Since we have 190 slides, it's taking a little while. Okay, just bear with me, and then that will be the end of this discussion today. Okay, almost there. So once we plot them together, we see that, like, let's say this is the 50 kilo electron volt boron. And what I see is it's kind of nicely matching up with the Gaussian distribution that I am able to extract. From where? We never went into the S trim part. Do you guys remember? We always use the trim part. In the S trim part, it gives me critical information about the Gaussian distribution, the fitting properties of these different implantations. So 50 kilo electron boron gives me this. Once I increase that to 300 kilo electron volt, it will penetrate more, as you can see. The phosphorus will stop here for 50 kilo electron volts. 300 kilo electron volts will penetrate more. And that's not even the end. So we will, of course, try to mask this with, let's say, we grow some silicon dioxide and we do our ion implantation. We implant both here, Gaussian, but we also implant into our silicon dioxide. So this is, the blue one is showing you right after the implantation, the Gaussian distribution inside the silicon dioxide. So you see, this is the silicon and silicon dioxide interface. If we, I mean, right after this, we have to put the whole thing into annealing, right? Because we'd like to repair the crystal. There's too much damage here on the crystal. If we put into the annealing process, but if we do not strip the silicon dioxide away, the Gaussian distribution of the ions will also diffuse. So instead of this staying like this kind of a confined way, the concentration will get relaxed and will propagate. And what's happening? They may propagate so much that they will start leaking under the silicon. So again, it might defeat the purpose. We might introduce quite a bit of significant contribution. Well, I look at the concentration, so there's not a big worry. I will just read them for you. Without the diffusion, it's like 8.7, with the diffusion, it's 8.7 times 10 to the 12 per centimeter cube. That's what becomes. Before the diffusion, it's 2.97 times 10 to the 10 over centimeter cube. So it increased 100 times the concentration, but still, you know, they're not really that drastically critical for the silicon crystal. All right, so that concludes this virtual lab portion together with the thermal oxidation and ion implantation. Yeah, and we'll see each other in the afternoon, and we will start discussing the deposition methods.
Okay, sounds good.
All right, so see you guys in the afternoon then at 1:30.
Yeah.
Oh yeah, sure, my pleasure.
She's doing a great job. Okay.